Hi. So last time, of course, we went through dimension, and we talked about the dimension of a vector space as being the number of elements in any of its bases. So naturally, the check-in asked some questions about dimension. Find the dimension, in this case, of each space. Okay, so let's have a whack here. So let's see. I'll just click that off. There we go. And so the first space is a plus bx plus cx squared, a plus 2b equals 0. So B1 is a plus things having trouble with the light. How's that? A little better? A little better. Is a plus bx plus cx squared, a plus bx plus cx squared, where let's see, it's a plus 2b equals 0. A plus 2b equals 0. Okay? And we've done these many times, so we're gonna do it again, I guess. So the idea here is you think of this as a linear system. It has only one equation, but so what? It's a linear system. A leads, B is free, B is not leading. So a plus bx plus cx squared, where a is minus 2b. We write that as minus 2b plus bx plus cx squared, where b and c are both free variables. And I like to break out the b's and the c's. I like to parameterize out, so we're looking at b times minus 2 plus x and c times x squared, where b and c are real, are free. Okay, so what we get then is we get a basis minus 2 plus x and x squared. Easy to check that it's a basis. I won't bother, but it's pretty clear this is the only one with an x squared. This is the only one with an x. So they must be linearly independent. So anyway, so it's easy to check that it's a basis. So we get dimension is 2 because there's 2 things in it. Okay, 2. Same problem, slightly different arrangement. V2 is it's the ABCDs, 2 by 2 matrices, where A is minus 2D and B is minus C. I already wrote them out as where the leading variables are expressed in terms of the free variables. And just mimic what happened upstairs. So A is minus 2D. So, forgive me, I'm misremembering. A is minus 2D, that's right. A is minus 2D, so I'm writing this as minus 2D. B is minus C. And C and D. Okay. I like to break out the D and the C. So C times 0, minus 1, 1, 0, and D times minus 2, 0, 0, 1, where C and D are free. And so I get a basis, B2. 0, minus 1, 1, 0, and minus 2, 0, 0, 1. It's easy to check that it's a basis. Linear independence obviously spans. There it is. It's spanning. It's easy to check that it's linear independent. So, I mean, look at the upper lefts, for example. It's easy to check that it's linearly independent, and so the dimension here is also 2. Okay, so dimension is just a question of coming up with a basis and counting 1, 2, 1, 2. Okay, let's talk then about the next topic. The next topic is we're going to circle back around and think about vector spaces and linear systems. So we're reaching back and thinking about linear systems again, only now we're thinking about it in the context of what we know now. So this going back and touching again what we had before is a very good technique, and we'll employ it a number of times in the course. Okay. So some words here. Now we're in the second chapter, so we can talk about vector spaces. The row space of a matrix is the span of its set of rows. The row rank is the dimension of that. So the row rank is the number of linearly independent rows. And the result here is that if two matrices are connected by some Gauss's method steps, then their row spaces are equal. That, as said sort of more sharply, row equivalent matrices have the same row space and therefore have the same row rank. Row equivalent matrices you get from one to the other by doing Gauss's method steps. Row equivalent matrices have the same row space and therefore the same row rank. Okay, and really the proof is all stuff that we've seen now, and we can apply the sort of relatively more advanced terminology and ideas to the stuff we saw in the first chapter. So we showed that when you have a Gauss's method step between A and B, then each row in B is a linear combination of the rows of A. So that is to say, in the terminology that we now have available to us, each row of B is an element of the row space of A. So the row space of B is a subset of the row space of A. Okay? And for the other containment that row space of A is a subset of the row space of B, remember that all of the Gauss's method steps are reversible. So if you have A connected to B by a sequence of Gauss's method steps, why then you have B connected to A by just the reverses. So you get exactly the reverse containment until you're done. So again, the result says that if two matrices are related by row operations, then their row spaces are the same, and so row equivalent matrices have the same row space, and in particular have the same row rank. So the next result is that the non-zero rows of an echelon form matrix make up a linearly independent set, and the reason is because we've seen it before. We didn't have the terminology in the first chapter, but nonetheless, the first chapter had this result that said no non-zero row of an echelon form matrix is a linear combination of the others. No non-zero row of an echelon form matrix is a linear combination of the others, and this is just a restatement. No one is a linear combination of the other elements of the space makes it linearly independent set. So time for an example. So this matrix before Gauss's method and after, so I did a couple steps, I'll spare you the arithmetic, have equal row spaces. If you can get some row vector as a combination of these three, then you can get that row vector as a combination of these two, and vice versa. The non-zero rows over here, or the top row and the second row, form a basis for that row space. So clearly it has dimension 2. So trying to understand Gauss's method from sort of this little bit higher level, I talked last video about trying to understand things first on a low level and then on a higher and then on a higher level. Okay, so we're now understanding Gauss's method on a little bit higher level. Gauss's method produces a basis for the row space of a matrix. Gauss's method produces a basis for the row space of a matrix. It looks at the span of the rows, winnows out the repeat information, and you end up with a basis when you throw out the zero rows. Okay? So I talked about row space. Next up I'm going to talk about column space. The column space of a matrix is the span of its set of columns, just like the row space of a matrix was the span of its set of rows. Column rank is its dimension. So that's the number of linearly independent columns. And why are we interested in column space? Why does that tie into what we've been thinking about? Well, excuse me. Here's a system, 2x plus 3y equals d1 minus x plus 1/2 y equals d2. And I'll ask myself, for which d1s and d2s can I find solutions? And we've certainly done that a number of times. And the answer is if there's an x and a y making this equation true. So that is to say, this system right here has a solution if and only if the d1, d2 is in the column space of this matrix. So we talked about this kind of stuff in the first chapter. When can you get a particular right-hand side? Well, we now have the terminology for it. When the right-hand side is in the span of the columns on the left. When the right-hand side is in the column space of the matrix. Just as a small aside here, I need the word transpose, so I'm just going to introduce it here. The transpose of a matrix is what happens when you interchange the rows and columns. And I use a superscript T there. It's kind of a funny font. Anyway, superscript T there for transpose. Authors do different things. Anyway, I use superscript T. I think that's pretty common. So column space is a vector space, so you can easily imagine being called upon to find a basis for it. We know how to find the basis of a row space. How do you find the basis? Because that's what Gauss's method does. How do you find the basis of a column space? Why, you turn the columns into rows. That's called transposing. Turn the columns into rows. See, the 2 minus 1 became the row 2 minus 1. The 3 1/2 became the row 3 1/2. Do Gauss's method, off you go. It didn't take very long because I'm not trying to illustrate Gauss's method, I'm trying to illustrate transposing. And now I have a basis for the row space, but the row space of this is basically the same thing as the column space of that, so there we go, transpose them back and you're done. I suppose I could introduce some kind of reduction method on the columns, but we already have a reduction method on the rows, so I'm just going to convert them to rows, do the reduction method, convert them back. The basis turns out to be the columns 2 minus 1 and 0 2. Obviously that's a two-dimensional, the basis is the basis for a two-dimensional space. Since R2 is a two-dimensional space, this must be the basis for R2. Okay, a couple more results that again circle back to the kinds of things we have observed earlier and try to put them in a context of the ideas we've expressed since. So, first, we have the idea in the first chapter that when you do Gauss's method operations, you preserve some things about the system. For example, you preserve the solutions. It would be pretty stupid to go through and solve it using a method that sometimes lost solutions. I urge you not to do that in the very first video. So here we go. We're looking for we're looking to say what's preserved. Row operations preserve column rank. Row operations don't change the linear relationships between the columns, so row operations don't change the number of linearly unrelated columns. What do I mean by row operations don't change the linear relationships between the columns? Well, I mean that if x times the first column plus y times the second column equals 3, 2, 5, and you do a row operation, you don't change that. That was the whole point of what we talked about in the first chapter. We're not changing the x's and y solutions. Anyway, so let's go to an example. In this matrix, the second column minus the first is equal to the third. So 2, 3, 6 minus 1, 0, 2 gives you 1, 3, 4, if I did it right. When you perform row operations on the matrix, the resulting matrices still has that relationship. So second column minus the first equals the third, that's right. Second column minus the first equals the third, that's right. Next result, a very often used result, that the row rank and column rank are equal, very often used in practice. Row rank and column rank of a matrix are equal. The number of linearly independent rows and the number of linearly independent columns is the same number. And the proof is, at this point we have a lot of machinery, so the proof turns out to be not many sentences. You bring the matrix to reduced echelon form, not just echelon form, reduced echelon form. Remember where you eliminate up as well as down. Then the row rank, of course, is the number of leading entries. That's the number of linearly independent rows is equal to the number of leading entries, because each of the rows in what's left has a leading entry. But the number of leading entries equals the column rank, because the set of columns containing leading entries is some subset of the EIs from a standard basis. Because when you do reduced echelon form, you eliminate up as well as down, and so all you have is a bunch of zeros with one single one in that column. That's an EI. So in the reduced echelon form matrix, the row rank equals the column rank. In the reduced echelon form matrix, the row rank equals the column rank, because each of them is equal to the number of leading entries. But we've shown that row rank and column rank are not changed by row operations. So back to the matrix where you started from, the row rank and the column rank are the same. So we use a single word for row rank and column rank. Just call it the rank. Rank of a matrix is either its row rank or its column rank, whichever one you prefer, whichever one is easier to compute. example. Time for an example. Although these are ideas we've seen before in a number of different contexts, the whole point of introducing them back again and again is to connect things together, because connections make the idea stronger. So here we go. I took this terrible mess. Look at that. What a disaster. What a disaster. How would you calculate the column rank? Well, the answer is do Gauss's method. Oh, look at that. Oh, anyway, it took me a long time. Anyway, I got it. I eventually got it. When you do Gauss's method, you get 3 linearly independent rows, and there's a 0 row. Since there are 3 linearly independent rows, the row rank is 3. But the row rank equals the column rank, so the column rank must be 3 also. In particular, can you see that 2, 0, 0, 0 is one element of a basis? -1, 3/2, 0, 0 is another element of a basis. 3 minus 7/2, 8/3, 0 is another element of a basis. That's 3 basis elements from among what amounts to sort of 3 tall vectors. This is essentially a 3 tall vector. Don't want to use the word basically. This is essentially a 3 tall vector. This is essentially a 3 tall vector. This is essentially a 3 tall vector. I have here 3 of what are essentially 3 tall vectors, so they span what's left. Anyway, the row rank and the column rank are the same. Okay, for a linear system with n unknowns and a matrix of coefficients A, then the two statements, the rank of A is R, and the vector space of solutions of the associated homogeneous system, it has dimension n minus R, are equivalent. So if you tell me that you have n unknowns, and then you say that when I do Gauss's method on it, the number of rows that remain, non-zero rows that remain, is R, then I can tell you that that you will have n minus R many free variables. If there are R many leading variables, there must be n minus R free variables, and so the n minus R free variables give you n minus R degrees of freedom. Okay, and again, we have all this terminology, we have all this technology, we're able to sort of tie it all together. So the rank of A is R if and only if Gaussian reduction ends with R many non-zero rows. And of course that holds if and only if the echelon form matrices are row equivalent to A have R many leading variables, and that in turn holds if and only if there are n minus R many free variables. Okay. And to finish, the last thing for today, tie this all together. Okay, where the matrix is n by n, then the following statements are equivalent. So, sometimes people in this class have not run across the following are equivalent before. Any one of these statements, any one of these 5 statements, is the same as saying any of the others. For example, if you say A is non-singular, that's the same as saying the columns of A form a linearly independent set. That's an if and only if statement. A is non-singular if and only if the columns of A form a linearly independent set. So I have 5 statements, each of which is equivalent to the other. Each of which is if and only if the other. Now you can go through and say, prove 1 if and only if 2, 1 if and only if 3, 1 if, but usually there's a shortcut, and in this case the shortcut is 1 if and only if 2, 2 if and only if 3, 3 if and only if 4 are all pretty clear. Okay, A is n by n, so if there are n linearly independent rows, if the row rank of A is n, then the column rank of A has to be n also, but A has n many columns, so they must form a linearly independent set. So you can see that 1 if and only if 2, 2 if and only if 3, 3 if and only if 4 are pretty straightforward. And the last one, if the columns of the square matrix form a linearly independent set, then any linear system whose matrix coefficient is A has one and only one solution. Again, it really ties us back to the very first day. Unique solutions for linear systems. And I'm going to say if the set of column vectors is linearly independent, then it's a basis for Rn. But then the system here has a unique solution for all choices of D's. Right? Has a unique solution for all choices of D's because we saw this result that if you have a basis, you can express the members of the space, true, 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 but you can express them in only one way. You express them uniquely. That's led to the definition of representation. Okay. Okay, very good. Now, that ends the second chapter. So I want to take the opportunity to remind you of two different things. So the first thing is, I should say first, congratulations, end of the second chapter. Great, 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 great celebration. So the first thing I want to remind you of is it sometimes is the case, if you're a person working on this on their own, it sometimes is the case that there's a tendency to leave the homework off and say, well, I watch the videos and I kind of look through the homework and I get it. And I can't overemphasize that that's not so. It would be way better to get all the homeworks and not watch the videos than vice versa. The homework is the point. The whole point of this is that you can answer questions about these systems. So if you find yourself saying, well, I can watch the videos sort of when I have a couple minutes of downtime, but doing the homework takes that a lot of extra time, so I have a tendency to watch the videos and not do the homework, please you know that that's not right. You need, the most important part is being able to do problems. Okay, that's the first thing. Second thing, I want to remind you that there are these videos on the internet I've recommended before by just look on YouTube, for example, by 3 Blue 1 Brown, and he does just a great job. He doesn't have associated homeworks or anything like that, but he does just a great job with fancy graphics and all kinds of things that genuinely aid a person's understanding of these things. And if you haven't been checking those out, look on his linear algebra channel. If you haven't been checking those out, please, I urge you to give them a look. They give a person an additional insight. In some ways, they're like the material that we did today. They take a person back and over the things that you saw before, but from perhaps some new point of view. And sometimes if you see the same thing from 2 or 3 different directions, it really reinforces what it is that you were trying to understand. Okay, very good. Next time we're going to start in on the 3rd chapter. Very exciting, starting on the 3rd chapter. So looking forward to that. Okay, all right, bye-bye.